professor in mathematics, all the faculty members, and the participating students. Today's webinar is on application of mathematics on science and technology. I would like to thanks once again, Odi Makinde sir and Ajit Kumar sir for accepting our invitation. Today's webinar is organized by Department of Mathematics, Dayanand College, Hisar. It is said that nature is written in mathematical language. Mathematics, computer science, and arts are related insanely. Mathematics is a tool to solve the problems of every other science. Realizing the beauty of mathematics and its application in every sphere, I would like to invite now Dr. Indrajit Singh, sir, Head of Department Mathematics, to introduce our resource person, Odi Makin.
Good afternoon, everyone. I am Indrajit, convener of this event, organized by Department of Mathematics, Dayanand College, Hisar, Haryana. I welcome today's worthy guests, Professor Odi Makinde, Dr. Ajit Kumar. I also welcome our source of inspiration, Dr. Vikramjit Singh, principal of the college, and participants around the globe. Mathematics is in many fields, including natural sciences, engineering, medical sciences, uh, finance, and other social sciences. Mathematics can, broadly speaking, be subdivided into the study of your quantity, structural spaces and changes, which are governed by arithmetic, geometry, and analysis. Today's international webinar is organized to enhance the conceptual understanding of the researchers and the students about mathematics. We focus on the role of mathematics in various scientific and technological fields, how to learn mathematics through new technologies and softwares will be discussed today. This webinar provides a platform to bring together leading scientists, researchers, and students from around the globe to exchange their knowledge. Today webinar have two sessions. In the first session, we have a keynote lecture delivered by Professor Odi Makinde on the topic magneto nanofield dynamics and engineering cooling applications. In the second session, we have our esteemed speaker, Dr. Ajit Kumar, Head Department of Mathematics from ICT Mumbai. He will deliver his talk on the use of softwares to solve the mathematical problems by using Sage Math. Now, brief introduction, Professor Odi Makinde. Professor Makinde is presently a professor of applied mathematics and computational mathematics in the faculty of military science, Stellenbosch University, South Africa. He is also a visiting professor of applied and computational mathematics in several other countries, including India, Tanzania, Kenya, Nigeria, and Ethiopia. Before joining the Faculty of Military Science, Stellenbosch University, Professor Mike Makinde already worked as senior professor and director of the postgraduate studies and the founding director of the Institute of Advanced Research in Mathematical Modeling and Computations at the Cape Peninsula University of Technology, South Africa from 2008 to 13, and full professor and head of the Applied Mathematics Department at the University of Limpopo, South Africa from 1998 to 2008. Now the awards and honors. Professor Makinde is the recipient of 2014 Nigerian National Honor Award titled MFR for his outstanding contribution to mathematical sciences and contribution by His Excellency, the President of Nigeria. He won the prestigious 2011 African Union Kwame Niruma Continental Scientific Award from African Heads of State for outstanding contribution to the basic sciences, technology, and innovation in Africa. He is also the winner of five more scientific scientist awards between 1990 to 2019. Professor Makinde received a prestigious fellow of the African Academy of Sciences in 2012 and fellow of the International Academy of Physical Sciences in 2018 for his outstanding contribution to the mathematical sciences. Professor Makinde is on the editorial board of several reputed academic journals and also served as the reviewer of the for many reputed international academic journals worldwide and for the NRF. He also authored four textbooks of monographs on the particle mechanics and incompressible flow theory and published over 400 research papers in many reputed international journals. His research covers a wide range of topics including fluid mechanics, nanofluid dynamics, heat and mass transfer, hydrodynamics, stability, dynamical systems, biomathematics, and many more. The main objective of his research to use mathematical theories and methodologies to gain insights into the dynamics of various engineering and biological systems that are of industrial and environmental, medical and social interest. Professor Makinde's research has contributed immensely to the upliftment of many African scholars in the field of mathematical sciences, research, postgraduate training. He has supervised over 32 PhD scholars. Now, I would like to invite our worthy principal, Dr. Vikramjit Singh, for the formal welcome of the chief guests. Sir.
Good afternoon, everyone. I formally welcome our today's esteemed guest, Professor O.D. Makinde, University, South Africa, and Dr. Ajit Kumar, Head Department of Mathematics, ICT, Mumbai, on the International Webinar on the topic application of mathematics in the science and technology on the behalf of the Dayanand Colleges. Sir, although I'm a student of political science, but I know how much important is mathematics in our life, specifically in the science and technology. So today we have two dignitaries with us to enlighten us on this topic. And now I invite Professor O.D. Makinde to enlighten us on this topic. Please, sir.
That thank you very much. I'm very grateful for the opportunity you have given to me to share some ideas on some of my research with you. And as you have been informed, the title of my talk or my presentation is basically on application of mathematics to engineering problems. And I'm going to start the presentation by first appreciating the proprietor and the principal of the college for inviting me and the management of the institution to deliver this webinar to my colleagues. And it's a way of improving the mathematical strength and the way of sharing knowledge across the continent, even in the midst of what is going on, this global pandemic that is causing disruption in academic environment. So we also thank God for sparing us, for keeping us safe throughout this period that all these things were going on. So we really thank all the audience who are volunteers to also be part of these important events of sharing knowledge. Without wasting too much time, as you have seen the topic, Nano Fridge dynamics and its engineering cooling applications. You will see clearly that the topic deals with the dynamics, and dynamics, in fact, is talking of mathematics. And the nano fluid and magnetic field you see there, and the engineering, they are both combined to show you how dynamics in mathematics can be used to gain some insight into the operation of engineering system and to improve them. So my talk and my presentation overview is as follows. The introduction, the applications, literature review, fundamental equations, model formulations, numerical approach, numerical result, conclusion, and references. All these will be described in my presentation. Now, let's start with the introduction. The introduction part is just to describe to you what is a stagnation flow. Engineering cooling is closely associated with stagnation flow. That is, what do you mean by stagnation flow? When when you put a liquid, you put them on the surface to cool a surface, a cold liquid. What you are actually doing is you are using that liquid to take out the heat from the surface. If you see this body, this black body here, the black body you see here is very, very hot. And when the body is hot, you see the movement, that green movement. It talks about the motion of the fluid towards this body. And when fluid moves towards the black body, you can see that it flows around it. And in that process, taking out the heat, there is a point of impact here where the fluid becomes static before it starts spreading. That point is called stagnation point. You can see from the diagram here, from this figure, you can see you put suppose this plate is very hot, and you put a fluid on top of it to cool this hot plate, take out the heat from this hot plate, to cool this hot plate. As you are pouring this liquid or the fluid on top of this surface, it will hit a point. After that, it starts spreading across the surface. That point where the velocity becomes zero before it starts spreading is called stagnation point. So cooling system in engineering always embedded with stagnation point. That is the point of contact between the fluid in motion and a stationary body. Now, from there, it starts spreading. So it has to do with the dynamics of the fluid that is being put on the surface, especially when it comes to banding layer. So the surface in contact with the fluid forms what we call a banding layer problem, which means there is a thin layer of fluid attached to the surface, whereby if the surface is moving, that thin layer moves with the surface, and the surface is stationary, that thin layer sticks with the surface. And that is due to the viscosity of the fluid anyway. So this is what we are going to describe in terms of dynamics. And if you look at the surface as well, you see when a fluid is used or a liquid to cool a surface, it depends on the nature of the surface. If the surface is very slippery, then when the fluid hits the surface, there will be what we call slip condition. Slip condition means the surface is slippery. But if the surface is not slippery, then you have what you call no slip condition on the surface. That is, the fluid stick to the surface if you hit the surface, and those one away from the surface start moving. So those two aspects will be considered in this model and in this application. You can have a surface that is slippery, lubricated surface that need to be cooled. In that case, we apply what we call Navier slip condition. This is Navier slip condition. This Navier slip condition will enable us to take care of slipperiness of the surface. That is, this beta you have here is the slip parameter. You can see if beta is 0, it means the surface is highly lubricated and the fluid is pouring on the surface, so the fluid can slip on the surface. But if beta tends to infinity, then you have no slip condition. Both conditions will be looked at in the dynamics of the cooling of engineering heated surfaces. So those are the things we have to take note. Also, we need to take note of the concept of boundary layer. The concept of boundary layer is closely associated with cooling of engineering surface. The concept of boundary layer. What is boundary layer itself? Boundary layer flow is the thin region on the surface of the body where viscosity or the viscous effect are very important, and that in the development, and that leads to development of momentum and thermal boundary layer. Or in fact, if your liquid or your fluid or your coolant, if contain some chemical, they can also talk of concentration boundary layer. So we are going to look at that thin layer close to the surface, where there is a variation in the velocity, temperature, concentration of the fluid that is using as coolant. So the concept of boundary layer is extremely important. So before you can model a problem that has engineering application with respect to cooling of the surface, you need to understand the mathematical concept of the boundary layer. What are the applications of boundary layer apart from cooling of surfaces? Then you can have the aerofoil when the aircraft is moving in the air. You can see the air resistance to the wing of the aircraft and the body of the aircraft is a kind of boundary layer problem, which also has application, because the air that is flowing around the aircraft forms a kind of boundary layer. The aircraft must be able to withstand the resistant forces, the drag forces, the frictional forces of the air, and otherwise it will blow away. So that is also very important. In the ship, when ship is moving in the big ocean, the body of the ship must be able to withstand the water resistance as it's moving through the ocean. So it's also the surface is an interaction between the surface and the fluid, which is also a concept of boundary layer. Also turbine blade, fan blade, industrial cooling of all surfaces, which we are actually talking about in this presentation. So the concept of boundary layer, as you know, was originated by Prantl, and Prantl developed it, and we also have Blasius, who also work on the concept of boundary layer. Blasius is a graduate student of Prantl. So the work on the concept of boundary layer, you see, he was able to bring about what we call similarity variable that you can use to reduce the momentum equations, especially the Navier-Stokes equations, into from PD to ODE, and enable him to be able to obtain the solution of the velocity profile, the boundary layer, or velocity boundary layer thickness, or momentum thickness, and the displacement thickness around the flat surface. So those are the concepts in brief of boundary layer, which is very, very important where you have a fluid in contact to the surface with respect to cooling or cooling of surface, and it's taking out the heat the surface. And you know, extremely important, cooling of surfaces. I will show you some of the applications in engineering. Also, what is nanofluid? As a part of introduction, nanofluid is just basically a mixture of nanoparticles and base fluid. You know, when you want to cool a surface, it is well known that you can use a conventional fluid to cool a surface. like conventional fluid like water, oil, ethylene glycol, polymer, solution, biofluid, and so on. All these are liquid or they are fluids. When you put a fluid on the surface or a liquid will take out the heat. But the problem is that liquid can flow, but the thermal conductivity of liquid or fluid is very, very low compared to solid. Solid like metals, oxide, ceramic, metallic carbide, nitrite, non-metallic carbide like granite, carbon, nanotube, and so on. All these metallic materials, they have high thermal conductivity. They can conduct it, but the problem with them is that they can't flow. They cannot flow. They cannot move. If you put a metal on the plate, on the surface, that metal can take heat from the surface by conduction. But the problem with the metal is that the metal cannot flow across the surface. Meanwhile, if you put a liquid can flow across the heated surface, but the thermal conductivity of the liquid is very, very small. Therefore, in 1995, there was a research by Cho and his co-workers, experimental research, where they are able to fabricate particles of metallic particles or non-metallic particles of high thermal conductivities, and they fabricate them to nano size, which is 10 raised to power -9. They were able to, like a powder, like a powder like this. They fabricate them and they mix them just like 0.1%. They mix 0.1%. This is water. They mix it with water. And when you mix it with water, then you see the color change. 1% of this material mix it with water, you see the color. But they still remain liquid, but they mix them under laboratory condition. You can also take copper powder. You can mix them like that. Then they now realize that water, if you use it to cool a surface, the cooling rate of the surface, because of the low thermal conductivity of water, will be low and be slow. But if you put ordinary 1%, less than 1%, you put it there, the rate of cooling, of taking out the heat from the surface will be higher than when you use ordinary water. And the water can flow. This liquid now is a solution. It of water and this less than 1%, and 1%, you have 0.1% and also 1%. When you put them, they see a big difference in the cooling rate. The cooling rate and the rate of taking out the heat has increased by almost 30% instead of using ordinary liquid, and without damaging the surface. That brought about the concept of nano fridge. The nano fridge, the heat transfer capacity, heat transfer enhancement capacity of nano liquid is higher than ordinary UC-based fluid. And this has transformed the cooling technology in engineering industry, whereby you can lose the mixture because this can flow, this metal cannot combine their property. The best property of this in terms of thermal conductivity and the best property of the liquid in terms of flowing rate and everything, then you can get a very excellent coolant which can be used in cooling also, especially when you have a nuclear plant, you want to cool or a place that generates a lot of heat. Because if the heat is not taken out as it's being generated, it can lead to thermal runaway and destroy electronics, gadgets, and many things. So that is, you can see what I've talked about now. You can see this table, which you have here, this figure. You can see this figure. You can see that number 1 here is engine oil. Look at thermal conductivity. This is the material. The thermal conductivity, you can see increases. Carbon, you can see here, which is number 9. You can see the thermal of carbon is very high, and it's a solid, silver solid. They are solid material. Whereas when you look at the liquid material, engine oil, ethylene glycol, water, you can see very, very small. So when you look at, if you use this one as your coolant, 1 to 3, the thermal is very small. So the rate of taking out the heat will be very small. But when you combine this with some of the metallic particles here in nano size, then you can have a best coolant. So those are the reason why nano fluid is very, very important. And why do we need to know this? The physics of the problem we want to use mathematics to model, we must understand this properly before we can now model the problem. The question is, which particle and which nano and which base fluid will give us the best coolant? Will take out the heat more, or can we combine part of this part? And each of these particle, metallic particle, they have their advantage and they also have their disadvantages. We must take note of that, because some of these metallic particles like copper, silver, carbon, and so on, aluminium, some of them are not stable. They are not stable. They are not chemically stable, which means if you put a copper somewhere, it can be oxidized and become copper oxide, and the property of that metal, it decreases, it changes. You use copper, it become copper oxide. Meanwhile, it's not copper oxide, because it's oxidized. Same thing, aluminium can be oxidized, and so on and so forth. So, and the liquid cannot change. Liquid remains the same. So you have to manage their property to make sure you get what you want under laboratory condition and preserve them. And it has to nano liquid. So all these things will be looked at in the model. Now, these are some of the applications of cooling applications of nano fluid. You use it for electronic cooling. Electronic cooling, like all the gadgets, cell phone, all the radio, all the television, everything you have, nano liquid is used. Nano fluid is used in cooling. And the cooling system of electronics has been enhancedly improved because of the application of nano fluid in cooling this system. Otherwise, your system generates heat. Even the laptop you have is based on the application of nano. That's why you can have your laptop, the heat is being being dissipated and is taken away because the technology of nano fluid has been used to make sure that the cooling rate is enhanced in the electronics. Also, transportation. The car we are using, we have the coolant. The coolant you put in the radiator plus the water. You put water, you put the coolant. Or the coolant we are pouring to the radiator. There are applications of nano fluid. Coolant itself is a nano liquid. It contains some contain oil as a base fluid with water. Some also has a mixture. Some also have what we call some metallic, silver metallic particle, nano particle, and so on. So coolant you buy to enhance the cooling of the engine when you pour in the radiator is an example of nano liquid which can be used. Also, industrial cooling, you use nano liquid where you want to cast metal. When you want to cast metal, it's at very high temperature, and you want to shape it properly, you use nano liquid as well, and to make sure that the cooling and the solidification of the metal is regular, and you control the cooling. So the controlling of the cooling rate is where the magnetic field comes in, because you use magnetic field to control the flow rate, the cooling rate of a system. Because the fluid that you are used to cool is flowing across it, you can control the cooling rate. In industrial setup, they use this type of situation to nano fluid, and not only that, they use magnetic field to control the cooling rate. Also, medical applications, you can see all these in medical applications. You can see the nuclear plant cooling. Nano liquid can be used for nuclear plant cooling. I mentioned that. Also, medical, you can put nano liquid, nano particle. You can coat a nano particle with drugs for cancer treatment. So you inject that in the body, and when you get to the body, you use magnetic to direct it to the portion of cancer cell. With magnetic field, you can use it with the coated nanoparticle with the drug to destroy the cell of the tumor. The tumor cells can be destroyed using the concept of nano dynamics or nano liquid. So also in engineering, you can see, in military, It's used also in military. The concept of a nano liquid is used. You can see the applications that I put across here in military. Some of the military equipment, they generate heat, and when they generate heat, the heat must be taken out, and nano liquid is used to cool some of them. Otherwise, they will be thermal run away, and some of them will not be efficient in their operation. So nano liquid is extremely important. Nano fridge applications in military, in medical, for cooling of electronics, cooling of aircraft and transport system, industrial cooling, nuclear. Those are the applications of nano liquid. Many work has been done on this work. Even up to now, there are a lot of work being done. I told you in 1995, the experimental work of Cho, and which he was able to look at the combination, the laboratory combination of nanoparticle and base fluid to produce a high heat transfer enhancement fluid that can be used in engineering system. So after the experimental work, many theoretical work has been done. I did a lot of work also in the area of application of mathematics to the design of engineering materials that can be used in cooling heated surfaces. That is, in terms of application of mathematics to the dynamics of nanofluids and so on and so forth. So there are a lot of work done. Thousands of work has been done since that time and up to now. Let's go to the fundamental fluid equation in terms of mathematics. Before you can model problems in this area, first of all, you know it involves fluid, the title I put across. There are two basic concepts you must be fully aware of for you to be able to do something successfully in this area. The first concept is the concept of fluid dynamics. You must be very good in fluid mechanics, the continuum mechanics. That is one of the concepts. The other aspect, because I'm going to involve magnetic field into the problem, that means you must also be very vast with the knowledge, vast knowledge in the area of what we call electromagnetism. It's a concept in physics. The concept also in mathematics, applied mathematics, the concept of electromagnetism. So the concept of electromagnetism is very important, and the concept of fluid mechanics, they are both important. They are both concepts of engineering and concept of applied mathematics. And this concept will bring you the necessary mathematical tool that you can use to tackle this type of problem. Apart from that, you must be fully aware of the thermophysical properties of both the liquid you are talking about and also the nanoparticle material you want to use. So we have the continuity equation, which comes from the concept of fluid mechanics. It talks about conservation of mass. The mass in, mass out, they are equal. No, that matter is neither created nor destroyed. So continuity equation that is continuum, which means if a fluid flow into a tank and another fluid flow out, for you to know the amount of fluid in the tank, you subtract the one that goes out from the one that coming. You know the amount that's already in the tank. So there is continuum. You cannot have a vacuum. That's continuity equation. And when the fluid is incompressible, which means that we are talking of hydrodynamics now. We are talking of liquid dynamics. When the fluid is incompressible, then you are basically saying the density of the fluid is constant. The density of the fluid is constant or approximately or almost constant, because in some cases a gas can be referred to as incompressible under high pressure. When you compress it and the molecules are compact, they occupy volume and the space and their mass remain. Under high pressure, it's not that you can compress them further. Then you can say they are still compressible. So that's why you pump air to your tire, the tire of your car. You pump it and your car can, the tire of the car can carry the heavy load of the car, because at that point you can refer to your tire as incompressible. Although you can compress it a bit, but the compression is negligible. So that is, you can refer to them as incompressible, but what it means in general, the density is almost constant or is constant. That is mass per unit volume, almost constant or constant. Then you have the momentum equation. In this case, we are talking of Newtonian fluid, because you can have momentum equation for non-Newtonian fluid as well. The only thing is that you have it, the viscous term will be affected if you have non-Newtonian fluid. But we are talking in this case of the presentation, I'm talking about the Newtonian fluid and the momentum equation, which comes from the Newton's second law, F equals to ma. That is rate of change of momentum equals to the applied forces. So that gives you this. Then we have a body force, which is part of the applied force here in this case, which is magnetic field. And this force is called Lorentz force. Lorentz force is the cross product of the current density and magnetic field. The rho here is the density of the fluid. In this case, the density of nano fluid. Not that, because when you have liquid and the nano fluid together, there will be variation in the density due to the new solution you have. So you must take care of it by putting this there, rho NF, which will be density of nano fluid, which is a combination of density of the base fluid and that of the nanoparticle. This one is the dynamic viscosity, the new NF, and this is the pressure of the fluid that you put the pressure gradient that is making the fluid to flow, and so on and so forth. And these are the velocity vector V. So all these will be used in our moment for the fluid flow. Again, you need the energy equation. Come to the first law of thermodynamics, which says that when you have change of internal energy, it gives you the work done on the system, and plus the heat you transfer or you take away from the system is the third law of thermodynamics. And that you want to change a state from liquid to gas, from solid to liquid, you have to do work on it, and you have to add heat on it. So change the internal energy, give you that. So that produces energy equation. And this is what we call Joule heating. Joule heating is what is created when a liquid flow is subjected to magnetic field. Then you have Joule heating, additional heating that will be generated in the fluid, apart from the one due to physical dissipation, which is defined. And this Joule heating comes, and there can be another external heating, maybe source, can be radiation or whatever that can happen. You have this is a general equation you have, and this specific heat at a constant pressure, density, and this one for the nanofluid, and you have the T as your temperature. So this is thermal conductivity of the nanofluid. In this case, you are mixing that condition of the fluid, base fluid, and that of the nanoparticle mixed together. So you have that. So these are the equations we have. You must be able to derive this equation, to know it before you can model. You must be able to do the mathematics of it, the analysis of it. That's where mathematics comes in. But these equations are non-linear, they are basic, and the foundation before you can go into application of it. What of Maxwell equation? For those of us who are fully aware of it, the mathematics of Maxwell equation talks about the mathematics that involve in Am's law. Am's law talks about the current density, which you have there, and the call, we call it the call of the relation between current density and the call of magnetic field. That is what you have there, and you call it Am's law. And you also have Faraday law, which will change in the rate of change of magnetic field equals to the produced electric flux. That is, that when the magnetic field change, the electric field is produced. So you have that, and these are concepts in physics, in engineering, electrical engineering, and so on, which we need to take note because of possibility of what you call conductive fluid. Because this sigma is the electrical conductivity of the fluid. Like electrolyte, seawater, they are conductors. They have electrical conductivity. That's why they can conduct, they are susceptible to magnetic field. Any fluid that is conducting are susceptible to magnetic field. That the magnetic field can act on any fluid, not like it act on solid or metals. The same way, magnetic can act on a liquid that are conducting, and also create what you call a Lorentz force, depending on the direction of application of magnetic field. So this is very, very important. And we also have Ohm's law, which talks about the relationship between the current density by the electric field, and also the relationship between the magnetic field and the velocity. So all these will be used. We need this concept of electromagnetism to enable us to obtain our body force, which is Lorentz force here, and our Joule heating, which is this part. Anyway, that is the concept. These are the thermophysical parameters. If you want to model problem in engineering, you must take and work with engineers to know. And these are already in the books, or you can read it, or you can work with them, and you can do get the experimental results, which you have to put in the model. So you have pure water. These are the density of pure water, copper, and alumina. These are their density. On this density, you can take them at a given temperature. So you have averagely the density of these materials which you want to use, because they come in there, the specific heat at constant pressure for them, pure water, copper, alumina. I use this as a test case for my model. Then you have this, the thermal conductivity also is given. You can see copper. That copper is very, very high compared to alumina. Compare alumina, which aluminum oxide, and they compare to pure water. So if you use ordinary water to cool a surface, the rate of cooling will be very, very slow. You mix them with this, it will take some property of this and this, then you have enhanced thermal conductivity of the nano liquid that you obtain. These are their electrical. You have this one as the electrical, conductivity of pure water, of these at different temperatures. You have this one for aluminum. So all this will be used. The physical property, the density of nano fluid, you can see, is 1 minus 5 rho F. Rho F is the density of the base fluid, and rho X is the density of the, whenever you see subject X, that talks about the nanoparticle. Subject F, that talks about the base fluid. And phi, which you have here, is the volume fraction, the amount, the quantity of the nanoparticle you use. You cannot use the whole of nano, you only small tiny fraction, less than 1%, because you can see if phi is 0, that means this part will be 0. You only have what? Everything will be nanoparticle. That means you have nanoparticle, and that will not move. If phi is 1, if phi is 0, this one will be, you have only base fluid, rho F. If phi is 0, this part will be 0. You have rho F. And rho F here means you only have base fluid. This gives you the density of the base fluid. That means your fluid will only be base, no nanoparticle. If phi is 1, this part will be 0. You only have nanoparticle. So to combine the two, you just need phi to be small. If you take phi to be 0.1, that means you are using 10% of nanoparticle. You are putting 10% of nanoparticle in the base fluid. If you use 0.1, 0.05, that means 5%, 0.01, 1%. Take 1% in the base fluid, then you will get the mixture. So phi value must be taken not more than 10%. That is not more than 0.1 to get a reasonable value of heat transfer, because increasing phi, then it will not be nano fluid again. The fluid will be so thick, be full of nanoparticles, then there'll be problem. So experimental work has been done that when you use nano, when you use nano particles, you take from 1% to 10% for you to get a reasonable heat enhancement increase. The same thing here, specific heat with density, the same thing, this relationship is what you use. This alpha here is the thermal diffusivity, which is density, thermal conductivity divided by this rho CPF, rho CP here, which you have here as the heat transfer specific heat of the system. So you have this. So this is thermal diffusivity. And the same thing with the magnetic field. This NF relates the base fluid and the magnetic field. All these expressions you have here are obtained empirically, which means through experiment and observations. So you obtain, these are from experiments. That is the relation between the thermal conductivity of nanofluid and that of the base fluid and nanoparticle. All these values are obtained. They are in the literature through experiment. And as a mathematician, you now need to use this thermophysical property relation and include and use these values which we obtain from the engineering experimental work and put them there, and now go back to your mathematics and numerics to obtain your result and test. What are the testing? Which one we cool better? Is it the combination of this and this, or this and this? And supposed to mix this with this, you have hybrid nano fridge and this. Will it give you a better cooler? So all these things, without going to laboratory, you can get results for that. And you can also see the transfer rate in all this. What is the effect of magnetic field? Will magnetic field affect this one more than this? Will this give a better result than magnetic field? Because magnetic field is important for flow control. If you pour a fluid to cool a surface, the fluid flow very fast. The heat will not be taken away quickly. But when you use magnetic field, it can slow down the rate of the flow rate, because the Lorentz force will oppose the flow rate. Depending on how you apply it, you oppose the flow rate and reduce reduce the rate so that the fluid can take out the heat from the surface more and better. So this is the model. You can see the model. This hot surface. You can see it's red. This is being heated up. There may be a chemical reaction going on, or there may be a kind of reaction going on here that's generating heat, or you can have a situation whereby nuclear reaction is taking place, generating heat. This is the surface you want to cool. Because if the heat produced, or maybe your electronics is generating heat, now you have to put a nano liquid. You pour a nano liquid here to cool the surface, like the surface of what do you call it? You can have a nuclear reactors. You can put that nuclear plants. So you want to cool it so that the heat generated are not accumulated. Because accumulation of heat can lead to explosion, thermal explosion, thermal runaway. So you want to reduce that. Even electronics. So this fire burning here represents heat generation. And heat generated here. This underneath is hot inside. So you cool from outside by taking away the heat. Now, magnetic field is applied in the positive y direction. You put this one, the fluid is being flown now, is pouring on it. There's a stagnation point here, and your plate also may be stressing. There may be a little stress due to heat. Maybe stressing, that is stress, or your plate may be shrinking. Stressing means the plate is stressed this way. Also, the surface of the plate, the upper surface here of the plate may be slippery. So we're going to consider when it's slippery or not slippery. What are the conditions? Or you may see a plate that is shrinking. This is shrinking, you can see. The plate is shrinking, surface is shrinking because of the heat, but this one is pouring on it, magnet is applied to make sure that the heat is taken. So all this, we want to look at it. And we assume the fluid that is flowing, steady flow, two-dimensional, incompressible. So to model this, you use the Navier-Stokes equation. It's a two-dimensional flow in X and Y. You have your velocity U and V. It's incompressible. You assume the fluid is Newtonian. Then if you do that, and you apply your similarity variables to it, to the general Navier-Stokes, and it's steady, you are going to get the OD that will come from it will be this. The third order OD will come where this A1, this model is similarity equation that we get. So what is actually happened is to apply it to this equation. You obtain this Joe ET, everything has been solved because I didn't go into detail of that, but I will just show you briefly how we obtain that. Then you have this equation. This one we call from momentum equation. And this one we call from the energy equation. These are in dimensionless, where your eta is a similarity variable in terms of the axial transverse distance. And also your F here now comes as a string form from the string function of the similarity transformation, where derivative of the velocity will be the derivative of F. Your A1, your B1, your M is the magnetic field parameter which comes, and this results from the Lorentz force which you have. there. And when you do the similarity, you are going to get this. In terms of the heat transfer from the energy equation is what you have here, where your A2, A3, A4, they come from thermodynamical property. PR is the Prandtl number. Theta is the temperature dimensionless variable. And you have all these we have here, and M is magnetic field parameter, which is the square of the Hartmann number. Is the square of the Hartmann number. EC is the Eckert number. And you know the product of EC and PR is the Brinkmann number. So all those ones, these are the boundary condition which we have. At the plate surface, that is here, where theta is 0, at the plate surface, you are having the velocity, because the plate is not permeable. You have the F of 0 is 0. Because the velocity at the surface here, if this, because the surface here may be slippery. If it's slippery, you are going to have this S. S is the slippery, the rate of slipperiness of the surface. And if S is 0, it means the surface is not slippery. Lambda here talks about the stressing. The stress, if lambda is 0, that means the plate is not stressed, it's not shrinking, it's not stressing. So if lambda here is positive, that means the plate is stressing. If lambda is 0.1, 0.2, it tells the rate of stressing of the surface. If lambda is negative, it talks the rate of shrinking of the surface. So, and all these cases will be considered. And this is the Bout number, this one. It talks about the rate of heat transfer underneath here to the, this is a cold nano liquid, coolant. This is a coolant. You pour on the surface, heat is there. So the rate at which heat from here is being transferred to the liquid up by convection, convective heat transfer below here, where it is generated to the surface here. This is what we call here, this Bout number. If BI is 0, that means that this is adiabatic. That means the heat here cannot go, and that is very, very dangerous. Because it will be accumulated here. This cooler will not take away any heat. So every material, they have heat transfer coefficient. They have the rate at which it can pass through them. And a metallic material or a surface, like you pour a water in the cup, you touch the mug. You can see the mug is very hot outside, it's warm. That means it can go through the mug where you put the hot water. So the same thing, nuclear reactor, their surface inside, where the reaction is taking place inside their surface outside can be hot. So you have to take away that heat. Then you see the smoke coming out, the heat is being taken away. So the rate of heat transfer year to year is BI, called Bout number, thermal Bout number. So as if BI increases, then more heat is taken from here, is going into the coolant, and coolant here, because it's a nano liquid, is taking it away, and this coolant is becoming hot. It's a cool that is loose, is taking it and losing it also at the same rate because of the nano liquid. It's high heat transfer liquid. So that's what we have. Then free stream, far away, yeah. You see, this is F, the velocity far away. We put it here. So this is the rate at which fluid is being pouring down at a uniform rate, pouring down this way. That is the free stream. Free stream is far away from the plate. So the boundary layer is this area, very close to the surface, where you have variation in velocity, variation in velocity profile. All these are boundary layer. Up here is free stream. Free stream. That is what you have. And that is, we want to look at what is the velocity profile here. How can we control its magnetic field? What is the effect of this fluid on the surface, the skin friction? What is the Nusselt number, the rate of heat transfer from coolant, from the hot here to the fluid? All this will be looked at, and temperature away from the fluid. Away here is hot, away we assume is cool. That's why you have the dimensional to be 0, but it's not actually 0. It's T infinity. That means temperature far away from at the free stream. So when you write the dimensionless, you have that. Anyway, these are what parameters we have there, which I've already explained. You have all these. These are B1, B2, B1, and A1, A2, A3, A4. They come from the thermophysical parameter which we have used in terms of nano fluid and the nanoparticle and base with their thermophysical relationship. So those are the parameters. And you have ECK number, bounce number, and all those I have explained them already. Still parameter, and 5 is the nanoparticle volume fraction. The skin friction is given like this. You work it out. Shear stress at the surface. Talked about this shear stress, the effect of the nano fluid on the surface. And this is not a number. The rate at which heat is taken by the base fluid at the surface. I mean by the nano fluid. The rate at which heat is taken. This is dimensionless. The heat flux in dimensionless form from here, from the surface by the how the nano liquid is taking away the heat, taking away the heat transfer from the plate surface to the nano liquid at this surface, which is eta equal to 0, is called what you call the Nusselt number in dimensionless form, called Nusselt number. Also, the rate of the skin friction. If you have skin friction, is the dimensionless form of shear stress. That is how this fluid is brushing the surface. Because this shear stress is very high also. That is rate of friction between the liquid and the surface. It can create damage on the surface. So you have to control that as well. So all this will be obtained. Now, take note, when you get this model and this body condition, you are now into mathematical realm. This is mathematics now. The physics, everything is ended. You have to solve this mathematics. All your mathematical methods, all your mathematical concepts now comes in. This is a non-linear problem because you see, it's not f and second derivative of f, dependent variable multiplier. So this is non-linear. You are squaring it. Non-linear problem. You can see also it's non-linear. These are non-linear problems and you have to solve it. And there are many ways of solving non-linear problems. You can solve them numerically, purely numerically. And to solve them purely numerically, you have to use method that will give you. Remember, all numerical methods are approximate method. But the best numerical method you use, the better the solution you get. Because each of them have various degrees of accuracy. So, but today, what you have to note is that there are many standard software which have incorporated highly accurate numerical methods like MATLAB and Maple. You have you can, if you look at this, if you can solve it with boundary value. You can find that difference method can be used, but the kind of finite difference method you will use will be the one of high degree of accuracy, maybe of order 4, order 5, order 6, order 7 accuracy. And look at it, a boundary value problem also. At 0 and infinity here does not mean infinity. It means where the free stream is attained. So you need to now decide that you can use finite volume, finite elements, whatever method you know. But the important is not the numerical method is a tool to enable you get the right answer. Like this problem now, if you solve it with a shooting method, because it's boundary value, you can convert, which is what or you can also use any method, but as long as your accuracy and the degree of accuracy is high in terms of the numerical, and numerical stability is taken care of, then you get the answer. So that is one thing you have to take note. Now this problem is solved when you solve them, the numerical approach, using shooting method, which means you convert the initial value, what you have here, the boundary value problem, converted to initial value problem, and use Newton-Raphson to determine the actual initial value for the unknown initial value, and use Rodriguez of order 6 to integrate them. Because when you convert it to initial value, then that means you have to solve them by numerical integration. And there are many highly accurate numerical methods for numerical integration. One of them is Rodriguez of higher order, order 6. You can even have order 8, where you are doing Romberg and all those things. Then you can do order 6, order 4, and so on. So all these will give you, focus of high accuracy, then you can get a better result. Newton-Raphson method also will enable you to get your known initial condition. Then you do that by shooting. And then you can integrate. First of all, you get the first set and you integrate and you use Newton every time to make sure that it converts, your proper initial condition converts for the unknown. So that is what you put here. You convert them and you put this here, convert them. These are unknown. This one is known from the problem. Then you can see this one is known. This one is not known, which is S3 here, which means the second derivative of the velocity, which is the derivative of the velocity. It's not given at the surface, which is actually the shear stress. So it's not given. So it's not known. And this also is not known. The temperature at the surface. We don't know the heat transfer, convective transfer across the surface. So all those you need now to find by shooting method. What shooting method means, you turn it to initial, you now obtain this using the known boundary condition to obtain the unknown initial condition by shooting. So all these can be done. And in MEPU, in MATLAB, Mathematica, and all those things, you can see there is a DDP and all those. So numerical method accurate can be done, and you can write your own code to do that as well for shooting. And this is not the only method to solve. I told you can use finite elements and all those things. You can now display your mathematical skill of numerical, and you can also know that this all numerical methods give you approximate results. You can also use semi-analytical method. Homotopy analysis can be used. Duration iteration method can be used. These are semi-numerical, semi-analytical method. You can also use homotopy perturbation method. You can use anomia decomposition. These are other new methods which people have developed, which are based on perturbation, but improved perturbation methods that are used to solve nonlinear problem. The only thing we get is that your answer also will be accurate to some degree, because you have to find the range of parameter value that your answer will be accurate. Because now you are using improved perturbation method. All these homotopy analysis, homotopy perturbation, and so on, they are improved perturbation. When you combine them with numerics, it also enhances your accuracy. But the result you get at the end, they are all approximation. But you can get results as accurate as a 10 decimal point, which is okay, and maybe 5 decimal points, 10 decimal points, you can get it accurate, and that is okay, and for engineering applications. So let's see the result. The result you obtain here, I will just go through it. You have conventional results, which shows you here now that look for copper water, for shrinking, when the plate is shrinking, dual solution, there are two solutions. There is dual solution where the plate is shrinking. That means you can have two solutions for shrinking, which satisfy the boundary conditions and satisfy the equations. So this is upper branch of the solution, lower branch of the solution. This tells you now that you can see as you are, this is negative, lambda negative. The positive side are for the stressing. This is stressing, the positive side. Tell you that the skin friction decreases as you increase the stressing. From 0 is when there is no stressing. There is no shrinking. The plate is stationary. It's not stressed, it's not shrinking. Negative here, for that you only have single solution. The solution here is not dual, it's only single for stress, for stressing. But for shrinking you have single up to here, but when you get to this level, minus this, the solution duplicates from here. You have solution here, you have solution here. At the same shrinking value, you can have solution here, you can have solution here. But in reality, that may not occur. In mathematics, it occurs. We call it bifurcation. So, and you can only have one solution. So when you do the stability of the solution, which I'm not presenting here, the stability shows that the lower solution branch is unstable. The real solution you will see in experimental work is the upper solution. So the lower solution branch, yes, it's part of the mathematical solution that satisfies the equation and boundary condition, but it's unstable. So what solution gives us here is that when you are shrinking, it will shrink to a point. There is a maximum value of shrinking. That is a critical point where your plate can shrink based on the nano liquid you use. You can see the shrinking here is minus this lambda C minus 1.274, which means if you use copper water nano liquid to cool your surface will shrink. The shrinking rate of your surface will be more than when you use aluminum. See, this one is minus 1.5. So you get to minus 1.25 before you get to minus 1.27. So this one is further. So the plate will shrink further depending on the nano liquid you use in cooling. So the shrinking rate of your surface will be more when you use copper water than when you use alumina. Your plate will shrink more. That is, and that tells you that copper water will take out more heat. That makes your plate to shrink more than when you use this ferrous oxide and water, or use alumina water. So we got that to find that. So if you want to shrink your plate to shrink more, then you use copper water compared to this. If you want your shrinking rate to be less, you use alumina water. So these are the shrinking and the mathematical concept. We were able to discover that after this value, there's no real value. The only real value you can get in that model is top here for lambda equals to minus 2.74 and so on, where you use copper. Below that, there's no solution. It gives you not a number, which means there's no solution. That means this is a critical point. It's a singularity. It's a singular point in terms of mathematical terms. After this, then you can be here you get solution, down there no solution. So that is what we have in that solution. And also dual solution, what is the effect of you can see here what is the effect of nanoparticle. As where zero means no nanoparticle. When no nanoparticle, you can see what we have here. Zero is this, the blue one. That means the critical value when there's no nanoparticle, when it's only ordinary base fluid, you can see the critical value is minus 1.2254. And when there's 10% of nanoparticle is 1.274. So increasing nanoparticle from 0% to 10% in your base fluid will increase the shrinking rate. The shrinking rate will be more. So that means nanoparticle enhance the heat transfer, cooling of the surface, and surface becomes shrink. If it is the surface that shrink, it becomes shrink. So it's shrink more, the critical value of shrinking is more. When you have the ordinary water, so using water, it will take less heat, and if you do 5%, you see minus 1.26. So the shrinking rate increases with increase in nanoparticle from 0 to 10% in the base fluid. So base fluid we are using is water for copper, and it also affects the other fluid. Also, you have the shrinking rate increase like that. What of the effect of slip? Where the surface is slippery, the surface is slippery. Then you can see where the surface is slippery. Where you have 4.1, you have the shrinking rate 1.08. Where is 0.4? So the more slippery, if the surface is slippery, the more the shrinking rate you have, the more shrinking rate you have. So the plate becomes more shrinking. It shrinks more when the surface is slippery. So the fluid can slip on top of it. And if less slippery, less shrinking. So that's what we're able to get, because the critical value for shrinking, for increasing the slippery rate, the rate of slippery of the surface. Then, so if you lubricate a surface and you are cooling it, the surface will shrink more than when the surface is not lubricated. That's what you can say there in terms of physics of it. The more slippery a surface is, and it's very hot, the more it can shrink. So those are the things we get. And also we have talked about this. So those are the things. Let's look at some solutions, the boundary layer solution. Boundary layer here for stressing, these are stressing. When you have stress, here I put my lambda here. Lambda is 0.1. And I use 10% of nano fridge. I'm using, I'm comparing copper, water, and alumina. You can see that the copper water is the dark or the dash. Alumina is the red. Copper water will move closer to the surface. You can see the boundary layer thickness of copper water. This is the surface, this is the free stream far away. You can see here, from here to here. Here velocity, this F prime is velocity. The velocity is increasing until you get to the, when you get to free stream, you can see it remains the same. So this boundary layer thickness is between here, you can see maybe eta equals to 1 point, almost 2. Let's say from eta equals to 2 here, downward. That's where you have variation in velocity, downward. That is momentum boundary layer. So this is the surface, that place surface at 0. So the thickness of boundary layer for copper water is smaller than that of thickness barrier for alumina, which means copper water get closer to the plate and take away and take more heat. So the lower the thickness of boundary layer, that is the size between here and here, the better the transfer rate, the cooling rate, because the fluid move closer to the surface and take. So this shows you now that the copper water, we have a lower boundary layer momentum boundary layer thickness compared to the copper water. Alumina water. So you move closer to the surface and take more heat. Why this one will move away from the surface and take less heat. So that is what he says. So that copper water is the best coolant to use. You can now see the other one is to see the slippery. When there's no slippery, when something is not slippery, that is 0. You have this. You can see the thickness between here and here. You see it's very wide. When we are increasing slippery rates, the thickness becoming small. The red one is when it's 0.3. It means a slippery surface will cool faster using copper water or any fluid. As nano fluid, we cool faster. Because if the spark is free, the fluid will move to the surface and move. Remember, we are using magnetic field also to slow down the rate of movement. When you slow down, so it makes it, although it's slippery through the surface, magnetic field is slowing down, so it's slippery. So that interaction will make it to take out more fluid, more heat from the surface. So the boundary layer, the momentum boundary layer thickness decreases with increase in slipperiness of the surface. So those are the things we have there. And you also see this one, magnetic field. You remember also the velocity increase because of slipperiness or because of the shear stress and the surface. And the surface velocity also increase. The movement of the fluid on the surface also increase. That's the movement here, but thickness decreases. Anyway, this magnetic field, you can see magnetic field tend to slow down the rate of movement by pushing the fluid towards the surface. Can you see? When fluid is 0, no magnetic field, when M is 0, no magnetic field, you have this one, which I call the blue one here. The blue one here is the first one, which means there is no magnetic field. When the intensity of magnetic field increases from 0 to 3, you can see the fluid is being pushed to the surface. So magnetic field, it pushes the fluid more to the surface, the nano fluid, therefore taking the heat from the surface. So that is the effect of magnetic field. It enhances the heat transfer rate. That is why it's good to use a conducting fluid. Conducting fluid with magnetic field enhance the cooling of the surface. That's why in the transistors, in the electronic devices, they have a magnetic field there, which control the flow, the flow of the fluid that is cooling the surface. And that fluid is nano fluid. So magnetic field is there. There is a kind of electromagnetism taking place. There is magnetic field generated there, which is imposed, and that is slowing down the flow rate so that it's making the fluid not to just be blowing out, to be moving. It touching the surface properly, take out the heat and blow it out. Without magnetic field or magnet in it to generate magnetic field imposed, then the cooling rate will not be efficient. So that is very, very important to take note. And also, this one is what I've explained. The negative here now tells you something. You can see negative lambda, talk of shrinking. 0 means no shrink, no stress. That means the plate is fixed, the surface. Positive means shrinking. You can see when it's negative, you have negative velocity. When it's shrinking, you have negative velocity. What does that mean? It means there is possibility of reverse flow. Negative velocity means reverse flow, flow reversal. Because the fluid wants to go in the positive direction, because the plate is pushing it back, shrinking, it's forcing it to reverse back. So the negative here, when you have shrinking, there is going to be a reverse flow reversal on the surface of the plate. You can see away from the surface, you can see everything is moving normally. From here, you can see positive. But when you get here close to the surface, there is flow reversal. And if you look at what I showed at the beginning, you can see it here. You see, plate is moving back, it's shrinking, there is flow reversal, here fluids continue moving normally on this side. There is flow reversal close to the surface. This is the effect of shrinking. And that's because plate is shrink. So you push fluid on top of it to shrink with it. Although within the bandy layer, some are moving this way, this plate is shrinking, then it's pushing it back, so there is flow reversal. That's why you see this one. Look at this one. For stress, everything is just moving this way. So that is just to show you the interpretation of that result. So your mathematics must reveal your physics of the problem. Similarly, for temperature, you have the heat transfer, the temperature increases with magnetic field. You can see this is due to Joule heating. You can see magnetic temperature of the thing increasing with magnetic field. Also, temperature increases with nanoparticles you put there. You can see increase in temperature of because the fluid become heated up, and you see the body layer. Also, you have this one. You can see for shrinking. For shrinking, what is this? Negative. You can see the temperature is very high. When it's stress, why? Because there is issue of interaction. You are having reverse flow and forward flow. Everything are interacting. Therefore, it generates more heat due to high shear rate. So you see that for shrinking plate, the temperature is high. For stressing, the temperature of the fluid is lower compared to when it's shrinking. And this increase in temperature is due to high shear rate in the fluid, because the one close to the surface is trying to move backward because of the shrinking, and this one, the fluid wants to move forward because of the issue of stagnation flow, and it's trying to move forward away from the other part of the plate. And shrinking also want to flow. There is high shear rate taking place, which creates more viscous dissipation in the system, and your additional heat and Joule heating as well. So these are the about number increase in the heat transfer from the lower part of the face to the upper part, increase in bout number, increase in the temperature of the fluid, and so on and so forth. Anyway, I've already mentioned this, the skin friction here. This one is for shrinking. You can see shrinking is when lambda is negative, stress in lambda is positive. So we've mentioned that. You can look at this that is when it's shrinking. Because shrinking, because of high shear rate, you have a high skin friction. For stress, you have low skin friction because it's not moving. High shear rate here causes high skin friction. And also you can see here also as you increase the nano fluid, particle of nano fluid in it from 0 to 1%, you can see skin friction also increase because the fluid become thicker because of nanoparticle. So the effect on the surface is higher. That's the disadvantage of nano fluid. It creates more skin friction because the fluid is now, it contains some components, particles, and also become thicker. The viscosity is higher because of nanoparticle. So the friction on the surface is higher. So that's why you see increase in nanoparticle, increase in skin friction, which is disadvantage. Although the heat transfer part of it gives us advantage for cooling. So nothing in life is totally 100% perfect. It has advantage. The advantage is that it takes away the heat very fast. But the disadvantage is that the heat transfer rate, the shear rate, the skin friction is high. So on the surface, it creates more friction. But that friction can be minimized based on the number of particles you use, and to minimize that. Anyway, that can take care. So these are just the results. Increase in bout number, you can see. Increase in bout number means increase in heat transfer rate from the lower to the fluid, or lower surface to the upper surface, and also as we increase the Eckert number. Eckert number talk of the viscous dissipation rate. The heat transfer rate may be decreased because of the combined effect of the combined effect of the magnetic field you have there. So the transfer rate decreases because you have the Joule heating. Magnetic field also is there, and you see that Eckert number also is the Joule heating, which you have to take, which gives you the Brickman number. So you have all these results. Let me go to conclusion because of the time. I've spent too many time now. The conclusion here is that nano fluid velocity increases from the wall towards the free stream. We bear that one, the velocity, nano fluid velocity, which means velocity bandy layer thickness of alumina water is greater than that of copper water. So copper water moves closer to the surface than the velocity bandy layer thickness decreases with an increase in the value of this parameter, which I've explained, the slip parameter, magnetic field parameter, the stress or shrinking parameter, and also the nanoparticle. The nanofluid temperature decreases from the wall. The temperature decreases from the wall towards the free stream. So you can see the nanofluid temperature. So you see the temperature decreasing from the wall toward the free stream, and you have the thermal bandy layer thickness for this alumina water is highest. You see, this copper water, thermal bandy layer thickness is highest compared to, or is higher than that of alumina, because it take out more heat, become more hot, and losing it to the ambient anyway. Thermal bandy layer thickness also increases with the Eckert number, the volume fraction, magnetic field, and the bout number, but decreases with an increase in the value of stress or shrinking, and also the shear, the slippery parameter. Skin friction increases with increase in the volume fraction and magnetic field. If you increase magnetic field, fluid push closer to the surface, therefore there is more skin friction, the more shear stress at the surface. Although it makes it to generate more heat as well, but decreases with increase in lambda and S. So dual solution exists for MAG nano fluid flow over shrinking. You have dual solution, and but that does not mean in engineering application you have two solutions. One of solution is valid solution. The other solution is a mathematical solution because it is unstable. We do the stability analysis of the two solutions, you will discover that. And how to do it, you can do the stability analysis, temporal stability analysis in time, and you put it there, you linearize, can do linear stability, you get it, and you see that the eigenvalue of what will be positive, the other will be negative. The positive, so that one, we have done it already, it's already, and so there are many people published on this. This one has been published already, so there's no big deal about it. So just take note of that. And Nusselt number increases with increase in nanoparticle volume fraction, stress shrinking parameter number, and surface slippery, but decreases with an increase in the value of magnetic field. So finally, to enhance the cooling rates at heated surface using nanofluid, it is advisable to regulate the values of various embedded parameters with respect to engineering and industrial applications. So those embedded parameters, the emerging parameters, they have to regulate it to the desirable rate, what they want to get out of the system. And the regulation in engineering is based on the design of the system itself, and that will tell you how to regulate and get which represent all these parameters we are having here. So that is these are so many papers and so on So thank you very much. Thank you very much. If you have any question, then we can talk about it. Thank you very much.
Good afternoon. Thank you so much, Professor Audie
Yes.
McKinday, sir. Nice talk
Thank you
on
very
magneto
much.
nanofluid dynamics and its engineering cooling applications. It's my privilege to have been asked to propose a vote of thanks on this occasion. I, on behalf of Dayanand College Hisa, extend a very hearty vote of thanks to Professor Odi McKinday, who blessed us with his presence. Today's session was quite insightful and comprehensive. I'm sure each one of us got to understand its importance of applications of fluid dynamics. As we all know that mathematics is undoubtedly a field that has a specific role to play in almost every area. So I would again to like thank you, Professor Odi Makinde, for sharing your thoughts on applications of mathematics. I'm sure that the information that you shared here with us today will prove to be valuable and worthy. Thank you, sir. So, this is not the end of today's session yet. We still have a lot of more to learn. So, I would now like to invite Dr. Ajit Kumar, Associate Professor and Head of the Department of Mathematics, Institute of Chemical Technology, Mumbai. He has completed his PhD in mathematics from University of Mumbai in 2002. Also, he has given his services in St. Stephen College, Delhi, and in St. Xavier Colleges, Mumbai, as assistant professor. He guided 15 master projects and one student for PhD. He has 12 publications in various well-known journals. Sir, as you are an author of six books, he has given several invited talks at national and international levels and also conducted several workshops and conferences for teachers and students over the years. He has been invited as a resource person in numerous workshops for teachers across the country. He has been a part of designing syllabus in many courses and have been member of board of studies of many institutions. I am proud to announce that his expertise in mathematical software like say Python, R, Mathematica, GeoGebra, Scilab, and many more. I would now request to our resource person, Dr. Ajit Kumar sir, to continue with today's session. Sir, welcome. Now over to Dr. Ajit Kumar. Thank you.
So thank you very much. It is my pleasure to be invited to this particular international webinar on applications of mathematics in science and technology. And I must thank the principal, Dr. Vikramjit Singh, the convener of the program, Dr. Indrajit, and all the faculty members of the Department of Mathematics, Dayanand College, Hisar. I would love to have been with you physically, but we are going through very, very tough conditions, challenges during this global epidemic situation. So never mind, I'm really happy to share my thoughts. And I must also thank the previous speaker, Professor Odi Makinde. He gave really very nice talk on how this nano liquid can be used in cooling in various applications, and how mathematics comes in this phenomenon. So let me begin uh, by saying that my talk will be slightly on lighter side. So what I'm going to concentrate basically on using some kind of softwares in teaching and research. So let me just give you a brief, let us say, introduction, if you may call it. So role of mathematics in science and technology. I mean, that's the more or less theme of the webinar today. And I think everybody knows the mathematics role in our day-to-day life. Maybe the general public are not aware. So as a result, if you talk to people, if you say that, okay, you are doing mathematics, they'll say, oh, you are doing mathematics, such a great subject. Oh, I was very good in school, but now I don't understand. Okay, so this kind of reaction is very, very common, right? So, so see, we can't imagine any science and technology without mathematics. Have you seen any, let us say, engineering course without mathematics? No. Everywhere that is common. Any idea, invention, or discovery somewhere involves mathematics. Gauss, a famous mathematician, once he had said, mathematics is the queen of sciences. I'm sure he must have some reason. And we all believe that, right? In fact, somebody also says mathematics is not just queen, it's a mother of all sciences. Traditionally, if you look at in India, mathematics is regarded very, very highly. Like all of you must have seen this sloka. Yatha shikha mayuranam naganam manyo yatha tad vedang shastranam ganitam murdani vartate. What is meaning of this? For Hindi audience, it is जैसे मोरों के शिखा और नगों में मणि का स्थान सबसे ऊपर होता है, वैसे ही वेद और शास्त्रों में गणित का स्थान है. In English, what it means? In English, it means that like a crowning crest of peacock, shining gems in cobra's hood, mathematics is permanently positioned at the helm of all sciences. So in India, not just now, but since, I mean, thousands of years, mathematics has been regarded very, very highly. In fact, I have grown up in villages, etc. People used to say, if you are good in mathematics, you can do any subject. I don't know whether that is still um, true, but this is what we used to think. Now, where do we see mathematics in our daily life? I think almost everywhere. Just now, Professor McKinday gave an application in industry, in defense, in medical science, right? So it is almost everywhere. You can see mathematics in nature. You see lots of pattern, and many patterns are due to Fibonacci sequence, golden ratio, lots of things. Even in our body, there is a Fibonacci sequence. You see mathematics in music, in art, in image processing, not just medical image, but any image you see, it is just a matrix, and all the transformations, etc., that you see involves very simple mathematics, right? Mathematics, after all, is studying patterns, connections, and any pattern that if you come across, it definitely involves mathematics. Mathematics is there in finance, not just exchange of money, but what happens in stock market. Everywhere you can find mathematics. In defense, in the security. These days we do, all of us are doing online transaction, and we do quite confidently. We are confident that whatever credit card, etc., we are using, it is secure. There is a mathematics behind that. In the sports, also you see mathematics, right? In fact, in the current world, we cannot just imagine this digital world without mathematics. The computer runs on binary system. You just think of when was the binary system invented. And was it invented so that one day it will be used in computers? No. It was purely an academic research. And now see what is its use. Okay. So though mathematics, it is abstract, it may look very, very abstract. It may look like it cannot have any applications, but you never know tomorrow there could be an application which is unimaginable today. So math is everywhere. Doing mathematics is actually fun, and it is beautiful. I'm sure you hear these words many times. But then when it comes to teaching or perception, people are afraid of it, right? Why is mathematics perceived to be a very difficult subject? Maybe there is something wrong the way we are teaching. I don't know. People are not able to make connections between mathematics and real world, between mathematics and technology. So one way possibly to bring out these connections, maybe we can use some of the tools that are available with us, some mathematical software. Maybe this can help, but it's up to us to find out how we use these things. There are numerous tools available which can be used in teaching and research. So when I say mathematical software, it includes very simple Excel spreadsheet program that can also do considerable amount of calculations. To big M, like just now Professor McInday talked about Mathematica, Maple, MATLAB, MathCAD, Sage, or even some of the mobile apps and online tools. I mean all of these. Anything that can help in our teaching is going to be good addition. And all these things are available very easily. Some of them are free, some of them are proprietary. It requires money, sometimes lakhs of rupees. But in case you want to use it, it is available. If you have money, you can buy big softwares. If you don't have money, still you can survive and do, and it will serve all the purpose that you want to. So there is nothing like how do I use it, where do I find it, do I have money to buy, etc. We don't have to worry about, right? So it is available very easily. Of course, then the question is, should we use these softwares in teaching and research? But when it comes to research, I don't think there is any debate. Nobody will tell that, okay, don't use in your research, because it is needed. You cannot, many things cannot be done without these tools. The research in mathematics and in many science fields have taken a new turn due to invent of computers and these softwares. But when it comes to whether we should use it in teaching or not, there is still some debate. Of course, in old days, one of the debate was, oh, these things are not available to everybody. Students cannot use it. Teachers don't have access to computers, to internet, etc. But I don't think such things exist today. Of course, still, I mean, to few it may not be accessible, but by and large, we are in very comfortable position, right? But of course, the question is, should we use it? If so, how do we use it? But then, as I said, if you are using this for your research, you are exploring these things left and right, why not in teaching? Can we still ignore this? I mean, I'm not here to pass my opinion. It is us to decide how you want to make mathematics teaching more effective so that you can catch students' attention. You can explain the connection between the concept that you are doing and outside world, its applications. And when it comes to this, I'm I think these softwares really will play a very important role. And it is not difficult to learn. It is quite easy. All you need to do is decide, okay, tomorrow I'm going to use it. I'll start learning. Okay, in the next course I'm going to use this software. I'm sure you will be able to learn. It it brings a lot of pedagogical benefits. I said you can bring out geometric idea behind the concepts. And of course, you can show the computational power, the, the kind of non linear equations just now you saw in Professor Markande's talk. It is just impossible to solve by hand. So you have to use numerical techniques. You need to code, right? You can bring in a lot of interactivity by teaching with pen and paper. When you're doing mathematics with pen and paper, you can do very simple thing. Whereas if you have these kind of tools, you can experiment, you can explore, you can create animations, and of course you can look at various applications. Students can be given some projects on which they can work, not just reading some books. Of course, that's also important, but they can be given some real life projects. And I find many times it builds confidence level of the students. When they create something on their own, they are very confident. Okay, I can also do it. Right? It is also very useful for people from other disciplines. They always need not learn the equations, the proofs, but in case they just want to solve it, they can just appeal to these softwares. So in that sense, it is useful. And all you know, when I'm teaching a class of, let us say 50 students, all of them are not going to become a mathematicians. We know that. But maybe some of them, maybe 20% or 10% of them may become, let us say, technocrats. Right? So the question is, how do we use it? That we have to be somewhat careful. I don't advocate that you just use it like a black box or use it like like an advanced calculator. No. Mathematics, first of all, has to be taught properly. But wherever we think that using these tools can uh, enhance students' understanding, that is where we should try to use it. Okay, so it should not be used as a black box. So teacher's role is very important in using these kind of tools in their teaching. One more thing I would like to just say here, that we should not just wait for making it compulsory by the administrator. I never had that kind of thing. Whenever I needed, Whenever I thought it can enhance the students' learning, I used it. Okay, so I think I've already explained. So this is just very brief introduction about why we should use mathematical tools, not just in mathematics research, but also in mathematics teaching. It can bring in a lot of pedagogical benefit. I have been using these softwares for quite some time. I do find it is really help. It really helps the student. So I'm going to look at few examples using a software called Sage, which is a free and open source computer algebra system. Let me just show you the website of the Sage Math. This is a official website of Sage Math, sagemath.org. And what does it say? Its mission is creating a viable free open source alternative to Magma, Maple, Mathematica, and MATLAB. And it is based on a programming language called Python, which is becoming very, very popular among scientific community, among data scientists, among web developers. I mean, you just name it. Almost everywhere it is becoming very, very popular. So this Sage Math is based on Python programming language. So anybody who is having a little bit of Python programming language would find it very easy. But to learn Sage, you don't require any knowledge of programming language. Without that, also you can very easily use this. And it is a free and open source computer algebra system. When I say computer algebra system, I mean a software which can solve numerical problems. It can deal with numerical solutions. It can deal with symbolic computations. In mathematics, we always play with symbols. Symbolic computations can also be done. You can plot graphs in 2-dimensional and 3-dimensional of almost all the standard objects. You can also write programs. So these are the 4 things that you can do in any computer algebra system, and Sage is no different. You have some of the standard computer algebra systems that you have are Mathematica, Maple, MathCAD, MATLAB, though MATLAB initially started with mainly numerical computation tool, matrix computation tool, but of late they have implemented symbolic computations as well. But all these are proprietary software you need to buy. Sage is available free and open source, and it has a lot of capabilities. Though some of the things may not be ready-made available, but you can very easily do most of the things with little bit of knowledge in programming. But without programming knowledge also, if you want to use it in teaching, you can very easily and use it, and learning also is quite easy. Okay, so let us look at some applications of Sage mathematical concept using Sage Math. But before I show you some applications, let me just very briefly tell you how you can use Sage Math. You can also use Sage Math online. You need not install in your system. So let me just what you see in my computer, that's a browser. Actually, it is a Jupyter browser, Jupyter notebook, in which you can write any Python code. and also Sage works in this. So what you see is an input cell, and of course inside this input cell can be converted into text cell. So in fact, this you can type entire your lecture notes in Sage, okay, including the mathematical results, its proof, graphs, plot, animations, everything can be in one notebook. So in that sense, it is very handy tool, especially for teachers. So let us see. Suppose I define a function. Let us say I'll define a function f of x. This is, let me just simply define x square minus, let us say, x into sine of x plus, let us say, exponential of minus x square. A fairly complicated function. Now we can ask what are the things that we want to do with these functions. Once you have this function, what are the things you would like to find out? Maybe you would like to plot graph. Maybe you would like to find derivative. Maybe find integral. Find local maxima, local minima of this. Find whether it has some real roots. Right? These are the things that we do in calculus. So all these things can be done very easily. How do we do it? Let me go to a next cell. So Sage, as I said, it is based on Python programming language, which is an object-oriented programming language. So there is a notion of methods, classes and methods. So if you say f dot and press tab, you will see all the options that are available that can be applied on f, including, let us say, differentiate, integrate, factorize, all such things are available. And let us say plot. I can simply say f dot plot, and you will see a graph of this function. You can see this graph of this function, though it has plotted between -1 and 1 because I did not mention the domain, but I can mention the domain. Let us say I want between -3 and 3, and let me say I want the color to be, let us say, green. I can even reduce the figure size. Let us say fig size, you can reduce it to, let us say, 4. That's it, right? So if you want to find what is the derivative of this function, all you need to do is again f dot diff, and that's it. You have the first derivative. Instead of f diff, if I instead of this, I can mention 2 here, then it will give me second derivative as a function of x. You can even find Taylor series expansion, right? And all these things, you don't have to remember all these commands. Just put dot and press tab, all the options will be available to you. You just don't need to remember. Nobody can remember thousands of syntax, right? So let me say, for example, you want to find, we can see there is a local minimum somewhere between -2 and 2. So if I say f dot and find local minimum between -2 and -1, it may take little, yeah, it has come. The minimum occurs as at -1.04, and the minimum value is 0.523, and so on. Okay, so all these things can be very easily done. Let me just give you one more example. Let us say we have a matrix, some matrix. Just choose a matrix. Let me say A is equal to, how about, I'll say random matrix, random underscore matrix, and let us say matrix over ZZ, and I want, let us say, 4 cross 4 matrix. Okay, and let us see what is A. This is A. Not only that, many of you might be using LaTeX for typesetting, for typing your mathematics, whether it is exam paper or writing books, etc. So Sage has very nice interface with LaTeX. You can create LaTeX code of any object that you use in Sage, and any LaTeX syntax you can put inside this notebook, right? So how do we do that? Let me just tell you. So suppose we have created this matrix A. Now I want a LaTeX code of this. I can simply say LaTeX of A. Here it is. Now in this code, you can type it in your LaTeX document, you can process it, and that's it. You have, so if you have done some complex computations in Sage, it is very easy to transfer or translate it into a document. And what did I say? In case you want to type mathematics inside this Sage worksheet, that also is possible. So let me put another input box here, and at the top you see there is a code. You can convert this into markdown, and then let me simply write that same matrix which we have got inside double dollar, closed inside double dollar, and then execute. Executing here is, you can go to the top and then press run, or you can simply press shift and enter. Here it is. You see now, this is the output. So it can interact very nicely with LaTeX. There is a Sage Tech package using which you can even call Sage commands from your Tech file. Of course, you need Sage to be installed in your system, but that facility is also there. Okay, right. So using Sage is very easy, and you can use Sage for doing calculus, doing linear algebra, doing even abstract algebra, number theory, graph theory, combinatorics, differential equation, even differential geometry. Most of the, and it can deal with even the abstract objects like finite fields, polynomial fields. All these things can be implemented. Okay, fine. So let us look at some 2-3 more applications. So let us look at Google page rank algorithm. We can't imagine these days, if there is no Google, there is no Gmail, etc. We'll feel that something is missing. So how does this search engine work? There is one of the first algorithm when this search engine was started, that is what is called Google page rank algorithm. So let us just briefly look at how it works. And this concept can be explained to anybody who just know what is a matrix and what is matrix multiplication. In fact, when I'm teaching linear algebra in first class, I give some of these applications, and it sets a platform. So let us see. So what I'm going to do, I will generate a random directed graph. So here there are 8 nodes, vertices, and 20 connections. And you can think of this as, let us say, a set of 8 websites connected to each other. Of course, there is no connection from one to another. Not everything is connected to everything. So not all websites are connected to each other, right? If that be the case, the connections would be much more. But this graph is a random graph, and that we have plotted using inbuilt Sage function. So you can see it uses graph theory. Digraph stands for directed graph, and random directed graph using some algorithm is what it is used. Right now, to this network, you can assign a matrix, 8 cross 8 matrix. Of course, we know in real world, millions of websites are there and they are connected. So if I have 1 million websites and I want to generate matrix for this, I have to generate 1 million cross 1 million matrix, which is very difficult to handle, right? So let us see how we are going to assign matrix to this. So in case you have studied graph theory, you must have studied what is called adjacency matrix. But what is it? In case there is a connection from J to I, you put that as 1, otherwise 0. So it is a 0, 1 matrix. Okay, so let us generate this. Okay, this is a adjacency matrix of this particular graph. You can check that in case there is a connect, for example, if I look at 6, 7 entries, 6th row and 7th column, right? So, but only thing you need to remember here is that in index in Sage, in Python starts from 0. So when I say 6, it will be the 7th column. When I say 8, it will be 8th column. So if there is a connection from 7 to 8, if there is a link from 7 to 8, sorry, 7 to 6, that means the 8, 7, 8th entry in the matrix would be 1. Let us see that. 7, 8, that's the one. This is 1. And there is no connection from 6 to 7. So 7, 6 to 7, there is no connection. So you will see that that one will be 0. Okay, right. So this is what is called adjacency matrix. Now what you can do, you can, each column you can divide by number of ones. For example, in first column, there is only one. From second column, there are 2 of them. In third column, there are 2 of them. So you divide them, and that will actually give you a probability matrix, right? So when I say 1 by 5 in this fourth column and third row, that means from fourth to third, the probability of going from website 4 to 3 is 1/5. That's what it means. So there is a probability of finding somebody on particular node. Okay, right. So this is very easily you can do. You can very easily do it with a small matrix, but if it is a big matrix, I mean computation will become difficult. Now the question is, suppose somebody start surfing this network. Let us say he starts with website 1, number 1. Just 1 second. He starts with surfing from second website. So that is the initial vector I'm calling, right? The question is, in long run, where can you find him? What is his probability of being located at a particular node? And that's exactly what you do in when you search. So when you type any keyword in Google, it goes through all the web pages. Of course, there is a server which does, because this crawling etc cannot, I mean real time, if it does, it will take a lot more time. So the the Google server at various thousands of servers are working, collecting all these information, and when you ask for in his keyword search, it gives you the first hit, which is the most appropriate one. Okay, but that means that that particular website will have rank 1. Okay, so if I click once, what is the probability of you being in various websites? That you can find out by just multiplying this probability matrix by this vector 0 1 0 0 0. And let me see, it says that on third website you have a probability of half, on fourth, fifth, sixth you have half, remaining 0. That is one click, right? If I want to know what happens to this, if I do about, let us say, 100 clicks. So how will I do? P to the power 100 times V, if I say, let me put this in numerical form. So it says that on first website, the probability is 0.22, not just 100. If I put 1000 times, you will see that it will be same. So you can find the rank of these. You can arrange this in decreasing order, and whichever has a maximum probability, that is the website which will come first. Okay, so this is very simple. I'm sure you can explain this to any 11th standard kid who knows how to multiply matrices. All I'm using is power of this matrix. But there are complications. First complication you can think of is, what if there are some website which is not connected to any link, which doesn't have any incoming link, right? Or doesn't have any outgoing link, right? So it, for example, when you open a PDF file, then that's it, right? So from there you cannot go to other website. You either have to click on back or type a new website, right? Or it's possible that you get stuck between two websites. So for that, Google has a way to modify this, and they call it is a Google matrix, right? So this probability matrix is converted into Google matrix, and the way it is done is that first you think of a matrix, probability matrix of all sides, all websites connected to each other. So everything will have probability 1/8. And then you take some kind of convex linear combination of this matrix, which is connected to everything, and the original one, right? So that matrix I called as a P, and then the second one, which in which everything is connected to each other, that I have called as S. So this is alpha times P plus 1 minus alpha times S. Alpha varies between 0 and 1, and it has been found by simulation that alpha is equal to 0.85, works very nicely. So this is what is called Google matrix. So instead of working with the original probability matrix, you work with this Google matrix that takes care of what is called the loop or dangling node, where you cannot, if you can go to one website, you cannot come back. Okay, so that takes, the Google matrix takes care of that, right? So now let us ask for, suppose I have, now we start with this fourth website, and try to find out after 10 iterations what will be the probability. So this is what you get. So for example, you can see here, the first one has maximum probability in this case, right? And instead of 10 clicks, if I want 1,000 clicks, this is what you get. And you can see here they will be very close to each other. If I have 10,000 clicks, again this is similar. And you can, of course, little bit of code, you can arrange them in decreasing order. So in this case, zeroth one, that is the first website, has highest rank. So this will appear first, followed by the fourth one, then the sixth one, and then the seventh one, eighth one, and then the third one, and so on, right? So this process is very simple. But then you can ask, what is the big deal about this? The big deal about this is, how does one deal with million by million matrix, which is the case in current internet setup? How does one deal with that, right? And how do we find higher power of a matrix, power 1,000 power, that you cannot do it by hand? Even computer will have problem. So that is where the diagonalization comes into picture. And how do we do diagonalization? Eigenvalues and eigenvector. Therefore, students should learn eigenvalues, eigenvector. Here you have a real life example of application of eigenvalues and eigenvector. And you cannot find eigenvalues, eigenvector analytically for million by million matrix. You need to do this numerically. So numerical analysis comes into picture, right? When you want to do numerical analysis, some programming language you need to know, right? So you see that this one example using this tool can explain lots of concept and motivate students why to learn eigenvalues, eigenvectors, and things like that. Okay, so this is you can look at this example and look at actually original paper by the inventor of Google, Larry Page and Sergey, I think, Brin, on Google Page rank algorithm, and try to understand. Of course, you can ask further question is here is, why does this always get into this stationary, get you this stationary vector? This vector is called stationary vector. When does that happen? Do I need some condition on a matrix? And the answer is yes, it does require. In case the matrix is what is called regular matrix, then this will always happen. Regular matrix simply means that all its entries are non-negative and some power of that has all positive entries. Okay, so there is a bit of theoretical aspect of it. Those who are interested can look into it. You can go through the stochastic matrices and the theory behind that. Okay, now let me look at give you another application. Image processing, right? Whether it is medical image, whether it is image coming from satellite, etc., you need to process. Many times these images are very, very high definition image. It may be very large size matrix. Dealing with that may require some efforts. For example, satellite, when sends its image to the ground, all these satellites will have very, very high definition, very good quality camera. So sending that image to the ground is an effort. So one way to do is maybe compress that image and send it. Okay, it will become faster and less cost. So that can be done using various things that are involved in image processing. For example, you can convert any image to any other image by sequence of affine linear transformation very easily. When you learn linear algebra and look at affine linear transformation, most often you will see that just as a definition and maybe work out one or two example. But it has lot of applications in image processing. How you transform an image, how you rotate an image, how you scale an image, all these things actually involves affine linear transformation. Similarly, affine linear transformation uh, has an application in fractals. Of many of you must have heard about of Sierpinski triangle. You can build that from affine linear transformation. So let us look at what is this singular value decomposition. So briefly, let me just explain. Any matrix you can split into U times sigma into V transpose, where U and V are orthogonal matrices and sigma is rectangular, but diagonal entries are only the diagonal rectangular matrix. Okay, of course the number of non-zero in this diagonal will be the rank of this matrix. Okay, those are called singular values, and it is arranged in the decreasing order of the eigenvalues. They will always non-negative, of course, right? And then if you write U as column matrix U1 U2 Un and V as, let us say, V1 V2 Vm, and then sigma this sigma as the rectangular diagonal matrix, you can write that as A is equal to sigma 1 times U1 V1 transpose plus sigma 2 times U2 V2 transpose plus dot 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 sigma R UR into VR transpose. Notice that U1 in the U1 will be M cross M matrix, V1 will be N cross N matrix, right? So this U1 times V1 transpose will be M cross N matrix. So and rank of this is going to be 1. So what you have done is a matrix A, you have converted into sum of rank 1 matrices. And also I said that sigma 1, sigma 2, sigma R are in decreasing order. And if you are dealing with million by million matrix, lots of the sigma i's will be 0. So all the, if the sigma is 0, that information is not there actually. So all these, the maximum information about this matrix is contained in first few terms. And that's exactly what is used in image compression. Okay, so you just take the image, convert into a matrix, and then find the singular value decomposition of that, and then just take first few of them, and that will be a very good approximation to the original image. But in terms, if you compare how many terms that original matrix has and how many terms that, if you take, let us say first, let us say even take first 100, it will, the difference is quite substantial. Okay, so that is an application of singular value decomposition in image processing. Now let us see how we can do this in Sage. Okay, so here is, I'm using matplotlib, a Python library, to read a matrix. This is an image. All of you know what this image is, right? Statue of Unity, right? So this is read as a matrix, and you can see here this image is plotted using a function called matrix plot. So two things: if you have any matrix, you can plot as a graph, and if you have any image, you can convert that into a matrix. So that is why I said matrix is nothing but, you can think of as an image, and image is nothing but it made of pixels that can be converted into a matrix. Okay, now what we are going to do, we will so I think these things I'll skip. This is red, green, blue channel. uh, okay, now let us transpose this matrix, because the third dimension here is for the image, the color, and then you apply singular value decomposition to this matrix, the compressed, the transformed image, right? It is taking little time because this matrix is of size 995 times 1770. That's a fairly large size matrix. So let us just uh, wait. Star means it is doing the computation. Okay, it has done. And you can see the U is now 3 cross 995 cross 995. This is the 3 cross 995. That is the S matrix, and this is the V transpose. Now we will with little bit of sigma, one has to transform into uh, 3 cross 995 cross 1770. And once you do that, now you reconstruct, multiply u times sigma times v transpose, and so that again multiplication is taking little time. Once you have reconstructed, now you can even plot the graph of, so this is the converted graph. Now this here it is using everything. Now let us look at, suppose we take only first five term in of this computation. So sigma 1 to sigma 5, and see how the, and then multiply rows, 5 columns of u, 5 rows, 5 columns of s, and 5 rows of v, right? And then see what the image you are going to get. So this is approximated. You can see here, this is let me say only 2 of them I am taking. You can hardly make out what this image is. But instead of 2, if I take 10 of them, 10 terms, you can now see this image is becoming much better. And in terms of size, it is quite significantly different, right? Instead of 10, if I take, let us say 20, if I take 20, now it is becoming almost clear. And let us say if I take 50 and then try to plot, this is almost very close to the original one. But the size it requires for 50 singular value is much smaller than the original size. Okay, so this is very nice application of singular value decomposition to image compression. Okay, and very easily you can do it in Sage, you can do it in Python, etc., very easily. Okay, so let me also show you one more application. Just now you heard a lot of uh, things about solving differential equation numerically, and one of the method that Professor Mackinday mentioned was RK method of various orders. So let me also show you one application. And these days in this pandemic situation, uh, you must have seen lots of articles and papers on predicting spread of this corona virus, various kind of predictions. And many of these, in case you have gone through a little bit inside those articles, there are few standard models. One of them is called SEIR, epidemic model. Okay, and that is nothing but actually a set of differential equations, ordinary differential equations. So here, if you look at these differential equations, there are 4 dependent variables here. T stands for time, X, Y, Z, and W. So here xt is susceptible population at time t, yt is exposed population at time t, zt is infected population at given time t, omega t or wt is recovered population. Of course, you can also include the death number of people who have succumbed to this, right? And here beta, sigma, and gamma, they are constants. Beta is called contact or interaction rate of the disease. Sigma is called transition rate of the exposed individual to the infected one, and gamma is called mean recovery rate. So these are the parameters here. Okay. Now suppose you want to solve this system, you can use uh, RK4 method. So I have written a small code for that. This is a very simple Python program. So once we have written this program, and you can see here the solution here is using DE solve system RK4 method. So RK4 method where the SAGE has all these inbuilt methods which we can use, right? And so it you have to feed in the parameters and the initial populations, initial uh, values. Now let us call these and see how the solution looks like. Let us plot the solution curve. So let us make use of the initial S init, which is the initial population of susceptible population is, let us say, 45,400, and then the other things, the initial values, and let us plot in 200 time, let us say 200 days, and beta, gamma, and sigma are taken these values, right? Now let us plot graph of this and see how it looks like. Yeah, so this is how the graph looks like. So this red color is the susceptible one. So you can see here initially everybody is susceptible to this disease, and then slowly it decreases. The exposed one, again you see how many are exposed, and that is again decreasing. The recovered one, initially recovery is small, but then it slowly increases. And of course you can ask, instead of using beta is equal to this, why use beta something else, then what happens? You can even create animations for this, and various parameters you can change and then show. Of course one has to also explain why this is happening. So when I'm using this kind of tool, very easily I can change these parameters on the spot and see what is the effect, which if I'm teaching using chalk and board, it will be very difficult. Maybe one or two graph I will just copy from something, let us say using Sage, and bring it in the classroom. Whereas if I'm using this kind of tool, then and there I can change these parameters and explain what is happening, etc. So let us just look at uh, mm, if I change, for example, let us say beta, let us say sigma instead of 1 by 10, if I make it 1, if I make it 1, and then see a lot of things have changed. Now, of course, as a mathematics student, you have to find out why such things are happening, right? But graphically, you can very easily compute using these tools. Let me change, let me keep this as 1 by 10, and let us say instead of 1 by 14, I make it 1, gamma equal to 1, and then see what is the, again, you see, this is a drastic change in the nature of the solution. So why such things are happening, that can be very easily explained using these kind of tools. Okay, so there are lots of applications that you can do. You can use Sage not only just in using in linear algebra, calculus, differential equations. You can also use it in your abstract algebra, in group theory. In fact, I have just finished writing one book on actually it is going to be published in just few days, uh, group theory with Sage. And there are also some more materials available on the website. There are some books freely available uh, for number theory, graph theory, for abstract algebra, etc. You can very easily learn from this. So let me just end uh, uh, this by giving you some reference. Of course, I could have considered many more applications, but uh, if you are interested, you can learn and create those applications on your own. Okay, so I don't want to just bore you with too many applications. So recently I have been giving a series of lectures on Sage Math. I have already just yesterday finished 11th lecture, and it is available on YouTube, so you can watch it. And starting from very basic, it has lectures on calculus, lectures on 4 lectures on linear algebra, 1 lecture on differential equation, and last 2 lectures will be on group theory. So one is over, one will be coming, and these links you can find out from my personal website, that is ajitmathsoft at wordpress.com /sage math, or you can Google it. I'm sure this uh, Google will be able to find it and give it. So thank you very much for your patient hearing. I think it is already 2.5 hours, so I'm sure all of you must have been quite exhausted, maybe. So let me once again thank uh, the organizers for inviting me to this webinar, and thank you all for hearing me out. Thank you very much.
Thank you, Professor Odi Makinde, Dr. Ajit Kumar, for your inspiring presentation. Your years of research, depth of knowledge, presenting the subject matter in the interesting way has produced one of the most memorable evenings. You told us about the various spheres where mathematics is used, and you also told that no field is untouched by mathematics. Thank you, sir, for sparing time and motivating us. I would also like to thank all the students who stood by us in this time. Thank you, sir.
Thank you. Thank you.
Okay, so thank you very much. So can we leave, or is there anything? Hello, Professor Indrajit.
Hello, sir. Yes.
Yeah, yeah. So done, right? I hope it was
Sir, very nice lecture. Very,
okay.
very informative and nice lecture. And
Okay, thank you
thanks,
very much.
Odi sir. Thank you very
Yeah,
much.
thank you. Thank you. Thank you very
I
much.
think we should end the meeting now.
Yeah, sure.
Thank you, sir. Thank you very
Okay,
much.
well, my pleasure. Thank you very much.
Thank you, sir.